In this second and final part of our introduction to the chemistry or chemical properties of the ocean, we're going to talk about the big three: temperature, salinity, and density. And before we talk about temperature, we need to sort of make the distinction between heat and temperature. A lot of people think they're the same thing, but heat is an energy concept. It's the energy produced by the random vibration of atoms, as it says there. Temperature is an object's response to the input or output of those vibrations. In our world, the world of earth science, we talk about heat budgets over the planet. The big one that you need to worry about is that there is a latitudinal variation in this. So if you think about the average heat across the entire surface of the Earth feeling those vibrations of energy in the atmosphere from those atoms, you can plot it up like this. So 0 degrees latitude is the equator, and the rest of this x-axis goes from the equator to the North Pole at 90 degrees north here, and from the equator to the South Pole, 90 degrees south. Now the tropics, 0 to 30, these are places where we have high solar radiation. They're warm. That's where you want to go for your vacations, your winter vacations. Get away from the cold. You go to the heat. They have a surplus of heat because they receive more radiation. The molecules are vibrating at higher speeds. As you go farther and farther away from the equator, you reach situations where there's less radiation, and so there's deficits. There's amount of heat that is less than the global average. So there is a transfer. This excess heat of the tropics is moved, literally a motion, to the mid-latitudes, to the high latitudes in both directions. This heat transfer occurs by the atmosphere. So if I were a climatologist or a person interested in meteorology, weather phenomenon, we'd emphasize the air. But for us, we're studying the oceans, so we're going to worry about this transfer of heat from tropics to higher latitudes by motion of water. This way, or here. This is the picture I showed before with the Gulf Stream. Notice it's going from the subtropics here, the warm Gulf of Mexico, Caribbean Sea, and the warmer colors, the darker colors are hotter. And notice it is moving upwards this way and mixing. We talked about this in terms of mixing time before, but you see it's a transfer of this warm reddish color water to higher latitudes where the predominant water colors are more bluish and therefore colder. Most of this heat is transferred by air. It's just easier to do. So these are, when you talk about the change of seasons, the motion of cold fronts, motion of winds, all of this, all of the stuff that is part of climatology, it starts with this transfer of heat. The remaining third of this transfer is involved with the oceans. We talk about this thing called heat capacity. Capacity in this context is how rapidly a object, a surface, a piece of matter can gain or lose heat. And land has a low heat capacity. It gets hot and cools down really quickly. So this picture of a pool in Arizona, if you think about a hot summer day in Arizona, the concrete around this pool is going to heat up scorching hot to the point, in just a couple of hours, to the point where it is so hot you can't walk on it with your bare feet. Or you can, but it's very, very hot. As soon as the sun sets, though, the concrete cools down very quickly as well. So it gains heat and loses heat rapidly. The pool, which is our analog for the ocean, will stay cold a long period of time. It can be 2 in the afternoon and this pavement is 100 plus degrees, super hot. The air in Arizona can be 100 plus degrees. The pool water is still cold. It's absorbing heat, but it's doing it much slower. It's doing it much slower. Fast forward to 8 o'clock, 9 o'clock, 10 o'clock at night. In Arizona, it starts getting cold there. The air is cold, the concrete is cold, the pool water is still rather warm because it's maintaining, it's holding that amount of heat. There's a clear distinction between the heat capacity of land versus ocean. This right here shows the average range of sea surface temperature and then the average range of land temperatures by latitude. And so here's how you interpret this. Let's go to the next slide. Oops, we gotta stay on this one. Land, notice that in the tropics here, you have the average range of temperature. It's hot. It's hot on land. That's it. So the range of motion is low. Same thing with the oceans, but there's variation with latitude. Let's look at temperatures plotted as this is degrees Celsius. And it's as expected. The tropics, more solar radiation, higher average temperatures, 28 degrees Celsius. As you go north and away, 25, 20, 15, 10, 25, 20, 15, 10, 5, 0. Beautiful paleolatitudinal distribution here, with some places a little hotter than others. There's 29 here in the Gulf of Mexico, and that's the site where the Gulf Stream starts that transfers this heat over here, and that's why there's this bulge. It's not just a straight line streaming across. These warmer temperatures are streaming up because of this motion of the Gulf Stream. Let's look at another factor, water density. Water density is defined this way. Pure water, just pure H2O, is 1.00000 grams per cubic centimeter. So if you had a perfect sugar cube size of water, pure water, it would weigh exactly 1 gram. But remember, we have water in the oceans plus all those dissolved salts. So we should expect our densities of seawater to increase, to be greater than 1.000 grams per cubic centimeter. Now this is going to vary in the ocean several ways. So salinity, the salts. If you add more salt to the oceans, this 1 gram per cubic centimeter gets heavier. So therefore, as salinity increases, the density increases. So we say that they are directly proportional. As one goes up, as salinity increases, the density of the water increases. Temperature is a different thing. Temperature is inversely proportional to this. So as the temperature of seawater increases, it gets hotter, it expands, it's going to make the density decrease. So you literally, in that little sugar cube of water, you're going to, because it's heated and expanded, you're going to have less actual amounts or numbers of atoms in there. So then the reverse is true. As you cool down, get colder and colder to the point of freezing water, the density increases. So think about it. If you have a sugar cube of ice versus a sugar cube of pure water, the ice is heavier because it is more packed. So it is inversely proportional. Here, as density goes up, temperature goes down. So these three factors are key things that we can look at around the globe and map this way. This is salinity around the globe, and you see, again, areas of higher salinity, the Red Sea, and areas of lower salinity here in Russia, here off the coast of South America where the giant Amazon River is flowing out. Variation. Here is a image of density of seawater, and notice now, remember, this is water plus salts. Pure water is 1.0, and if you add the saltiness of the ocean, you get numbers like this. This might not seem like much, but it's enough to make a big difference in the ocean. So here, again, this is latitude over here, and here's the surface of the water. The surface of tropical water, 1.0230. It is very close to 1. Think about it. The tropics have lots and lots of rain, lots and lots of fresh water running off there into the oceans. We've talked about that before. So there's less salt there. This is very light. As you go to these other places, let's say here at the 30s, remember we have lots and lots of evaporation, leaving behind lots and lots of salt in the ocean. And so the 30s approximately is where we have this 1.0270 higher salinity. But then highest salinity, and this is the Atlantic Ocean. So this is the North Atlantic, here's the Southern Atlantic. Off the coast of Antarctica, we have a situation where water freezes and creates giant icebergs and ice shelves. Well, that's pure water. That's not pure water, but it's fresh. The salt gets left behind in the remaining ocean water, making the ocean water around the Antarctic even saltier than anywhere else. Notice it is heavier, 1.0279. And what happens is you manufacture that super heavy salty water here, which is also the coldest, remember? And it sinks and it moves down across the ocean basin. Now look, it reaches into the northern hemisphere, and actually if it's mapped now, it goes even much farther. We call this phenomenon the Antarctic bottom water, where water that was at the surface in Antarctica over here is way down at the bottom, many thousands of miles away. And these layerings of the Earth's water are consistent around the globe. Well, again, we have lower density at the surface in the tropics because of rain and runoff. At the 30s, we have lower temperatures, but higher salinities because there's less rain and runoff. And you can do this, sort of map this, both salinities and temperatures in the oceans. So here's in the Pacific Ocean, temperature and salinity. And remember, as salinity increases, density is going to increase. So where you have high numbers here, you're going to have more dense water. But then you have the temperature effect, where the higher temperature waters make for less dense water, lower density. And then you have the Antarctic situation, where the temperatures are extremely low and the salinities are lower, but then they are increased versus the areas just north of them. So polar regions are very interesting. The temperature is very low. The density increases. We form sea ice, which is fresh water. The remaining water is saline, so it sinks. And here again is this representation. We also can talk about declines in the water. So look at the trends of temperature, density, and salinity with depth. The first one is the thermocline, this one here, notice it's the thermocline is the zone of rapid temperature increase. So we have high temperatures near the surface. So again, for these diagrams, the surface of the water is here. Here is depth. This makes sense. This is receiving the sun, solar radiation. It's hot. With depth, it rapidly drops off. And that's what the thermocline is. It's the zone of the ocean where the temperature rapidly drops. And then after the thermocline below, it's still dropping. But the change is very small with much, much greater changes in depth. There is something that we call the halocline, the change in salinity with depth, and that is the red line. Notice again here at the surface, because there is freshwater runoff, it is low. And at some point very near the surface, the salinity drops off. That's this halocline. Drops, reaches a point where it is relatively stable. And then we have what is called the pycnocline. If salinity and temperature are the things that determine what density is, then as salinity increases with depth and temperature decreases with depth, the density is going to increase with depth as well. So you have two factors that are acting to increase density with depth. We reach a point below the shallow surface water where the density rapidly drops, and then it remains stable with depth. This varies with latitude, this change of density with depth, change with temperature with depth. In polar regions, there's not much of a change with depth. In temperate regions, we have this change with depth, but in tropical regions, the red line, the thermocline is tremendous. You have a great drop from high temperatures in the surface to very low temperatures at depth. And notice at depth, below a certain depth of the ocean, let's say 1,000 meters, doesn't matter where you are. Polar areas, tropical areas, temperate areas, the water is sort of equally cold. This leads to the whole notion of thermohaline circulation. Look at the word thermo, temperature, haline, salinity. So this is circulation or movement of water due to changes in temperature and salinity. Now, this happens very, very slowly. So this is a hypothetical model of the ocean. Let's say it's the Atlantic. Here's a polar region, and the water there is sinking rapidly because of temperature and salinity reasons. So it's sinking. It moves down. There is what's called the deep spreading. Remember the Antarctic bottom water. And then it slowly rises far, far away, equator regions or even farther away. This vertical movement down and here, this spreading, is rather slow, 0.01 to 0.05 meters per day. Compare that to the motion or circulation at the surface of the ocean. This is horizontal. If you think of thermohaline as mostly vertical, even though there is a horizontal component at depth, it's vertical, dropping, versus surface motion, huge difference. Surface circulation, 1.5 to 2 meters per day or more. This is huge, huge difference. So slow here, motion here.